Hi, everybody. We're starting section 4.5, and this is a topic of basis and dimensions. So we learned the idea of a spanning set, meaning you could have a set of vectors where if you look at it could be a finite set. In fact, we're dealing really with finite sets for the most part, in this course. And you have a set of vectors. Let's say it's a finite set, and if you look at all the different linear combinations that could be churned out from this set of vectors, it winds up that you wind up getting every single vector in the entire vector space. So when that happens, we say that this set spans the vector space. We also had the idea of a set of vectors being linearly dependent or linearly independent. All that was from 4.4. Dependent means that it's possible to write one vector as a linear combination of the other vectors in that set. Independent means it's impossible. And there's other ways we defined it. Well, what if you have the best of both worlds? What if you have a set which spans the entire vector space and it is independent? If that happens, then you have something called a vector. Something called a basis. And that's what we have. That's what we're looking at right now. The definition of a basis, I'm just reading what it says in front of us. A set of vectors in a vector space is called a basis if it spans the vector space and if it is linearly independent. So these are the two features of a basis. So a basis has to have enough vectors to span the vector space, but not so many vectors that one of them could be written as a linear combo of the other. So in a way, it's kind of like an efficient set. It's just the right size. If it's too small, it might not span the whole vector space. If it's too big, then it could have more than enough to span the vector space. For example, if I have a set that's linearly independent, it spans the whole vector space, and I throw one more vector into that set, well, obviously that one vector can be written as a linear combo of the first vectors, because those first vectors span the whole vector space. Get it? Anyway, we're going to elaborate on that much more in much more detail. So let's move on. Let's look at just some. Now, as I said, you could have a vector space. You can have a basis with a finite amount of vectors. You have a basis with an infinite amount of vectors. But in this course, we're really going to be confining ourselves to the finite cases. Anyway, moving on. Let's look at some examples of bases. I'm never sure how to pronounce the plural of that. Bases. Now, here's the most simple. Let's look at R3. And this is like pretty much the most simple basis you could ever imagine. I have a set of three vectors here: 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, any vector that's in R3 can be let's say you have a let's say, for example, you have a vector, A comma B comma C. So A times this guy plus B times that guy plus C times that guy is going to give you the vector ABC. It's going to give you the point ABC. So that's so clearly and we showed this in the previous section that it spans R3, and also it's linearly independent, because if I look at this equation, C1 times the first vector plus C2 times the second vector plus C3 times the third vector equals 0, 0, 0. The only way this is ever going to work is if C1 equals C2 equals C3 equals 0, and that is, as I said, that was the official definition of linearly independent. So here we have a set of vectors which is linearly independent, and it spans, so it is a basis. We call this actually the standard basis. Now, notice that the standard basis for R3 consisted of three vectors. Get it? 3, 3. Is that a coincidence, or is it not a coincidence? Well, it's not a coincidence because if I want the standard basis for R2, it's going to have two vectors. The standard basis for R2 will be 1, 0, and then 0, 1. You get it? In fact, here we kind of generalize that right here. Look at what I'm looking at. If I have if I'm looking at N space RN, not RN registered nurse, but the set of all N tuples. Well, if I have 1 0 0 0 0 1 0 0 0 0 0 1, you know, this is going to be a standard vector for R3. So whether it's R2, R3, R4, R5, even R1, don't forget R1. Moving on. Now here is now not every, now basis doesn't have to be the standard basis. In fact, the word standard basis implies that there are non-standard bases. So let's look for one. So here is an example of a non-standard basis for R2. So here we have the set 1, 1, and we have the set 1, -1. So according to the definition, we have to show, of a basis, we have to show that this set spans R2, and then we're going to have to show additionally that it's linearly independent. So let's do one thing at a time. So let's verify first that our set spans R2. So let's pick a vector X, which has these two components, X1, X2, and that's just an arbitrary vector in R2. We want to show that the vector X can be written as a linear combination of vector 1 and vector 2. So if we show that any random arbitrary vector can be written as a linear combination of these two vectors here, that means that it spans the whole vector space. So let's say, so here's what we need to do here. We need to say C1, we want to find constants, so that C1 times vector 1 plus C2 times vector 2 is equal to this vector X. And you see, and it won't even matter what the vector X is. So we get C1 times 1, 1, C2 times 1, -1 equals X1, X2. It's all good. Now, the first component of this vector is C1. First component of that vector is C2. So the first component of the combined is C1 plus C2, comma. Now, comma, the second one is going to be C1 and then -1 times C2, C1 minus C2. And that's going to equal my X1, X2. Now, by the way, notice that they didn't tell us what X1 and X2 are. We just wanted to, show that we could find them. Well, this clearly has one and only one solution. Why? Because the coefficient matrix has a non-zero determinant. 1, 1, 1, -1. The determinant of that is -2, which is not equals. And I don't care what the determinant is, as long as it is not 0. So I have a non-zero determinant, which means that no matter what the X1 and the X2 are, no matter so I can pick any vectors in the world, no matter what numbers you pick for X1 and X2, I will be able to solve this equation. And I know that because the coefficient matrix is non-zero. So there you go. Now, I just want to say another thing. Let me just put it right here. So I just want to show also, I want to say also that we see with like good old-fashioned high school algebra, we could see that if I would add these two equations and divide by 2, I get C1 is equal to X1 plus X2 divided by 2. And if I subtract these two equations, I get C2 is going to be X1 minus X2 divided by 2. So again, this is just like an algebra. Just with old-fashioned algebra, we could see that this is going to work. All right, so we're all good. Yay. What if I could highlight it? That would be interesting. Could I highlight that? That would be cool. Yes, I can. It's wonderful. I like highlighting things. Makes sense. Okay, let's shut that off. So moving on. That's so now we know that this set of vectors spans the vector space. So any vector in R2 can be written as a linear combination of V1 and V2 and V2. Now we have to show that the set S is linearly independent, and actually that's kind of the same thing, because if we go through the whole same process here, and we get this matrix, well, the fact that this coefficient matrix has a non-zero determinant, which we already established up here, we mentioned that already. Well, that means that it's linearly independent. It means that that the only solution is the trivial solution of C1 equals C2 equals 0. And that means S is linearly independent. So we have a set of vectors here. It's a small set, it's just two vectors. And these two vectors form a basis, not the standard basis, but it forms a basis for R2. That's what we want to show. So we're happy. Yay. Let's look at another example of a non-standard basis. And that is this guy right here. 1, 2, 1, 1, 2, 3, 0, 1, 2, negative 2, 0, 1. So we want to show that this is a basis, which means you want to show that it spans the vector space R3 and it is linearly independent. So which would mean that S is a basis indeed for R3. Well, whoops, what just happened here? And this is something that we actually have done this already, because we've already shown from previous examples of the previous section. In example 5 and example A, if you look at the previous section, we showed that this set of vectors does span all of R3 and is linearly independent. So this is indeed a basis for R3. Now let's look at another example. Let's look at a basis for a vector space of polynomials, and let's look at the vector space P3. P3 means all the polynomials which are degree 3 or less. So let's look at the set 1, x squared, x to the third. Well, this is actually going to be a standard basis. Not only will this be a basis, but it's really going to be the standard basis. If I have a polynomial a0 plus a1x plus a2x squared plus a3x cubed, and the a's are all real numbers, well, this is precisely the form of all polynomials in P3, and we want to verify. And but these are the four vectors here. A0 times the vector 1, A1 times the vector x, A2 times the vector x squared, and A3 times the vector x cubed. So basically, I just took linear combinations of these four vectors. I'm calling them vectors now because we're viewing them not as polynomials. We're viewing the polynomials as elements as members of a vector space. Everything depends on, of course, on how you view it. And I basically churned out every polynomial in P3. Now, to verify the linear independence, that's also going to be pretty easy. So first of all, we know that the 0 vector is part of P3. And the polynomial 0 of x is just equal to the scalar 0 for all values of x, for all x. Notice that that's a bold at 0, and that's a non-bold. The bold 0 means the vector, the 0 vector, the 0 polynomial, which is the 0, which here is a 0 vector, and that just means the scalar, the number 0. Anyway, so the test for linear independence gives us this equation: a0, a1x, a2x squared, a3x cubed is equal to the 0 vector. Not just that it equals 0, but it equals 0 for all x. So we have a third degree polynomial, which is identically equal to 0. The word identical here means that it's, the word identical means that it equals 0 for all values of x. Not just I could find values of x that make it equal 0, but every value of x makes it equal 0. And from algebra, we know that means that all the coefficients have to be 0 for that to happen. And pal, so we've done it. So we've shown, which means that that's the only, the trivial solution is the only solution, and yada, yada, yada. So it's all good. Now let's look at another kind of basis. Let's look at basis for M22. This is the set of all, what's M22? That's the set of all 2x2 square matrices. Well, again, this is going to be a standard basis. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Basically, this is going to be the standard basis, and you can basically show the same way that it is it spans and it is linearly independent. Now Similarly, I don't have to confine myself actually to square matrices for this last example. I could have a matrix with a dimension where there's m rows and n columns, where m like Mary, n like November, and they're not necessarily the same amount. But I could do the same thing. Just have a whole bunch of matrices and just put a one in each a one in each position, and I get. Notice here it says I get m times n. Like if these are 2x3 matrices, I just have to get 6 different matrices. Each one is going to have each matrix is going to have a 1 in a position, and zeros everything else, and I just go through all those 6 positions or the 6 entry positions in this. Anyways, let's get to a really, really super duper important theorem, and that's theorem 4.9. And I want to be very clear what it means. First, I want to be very clear what it means and what it doesn't mean. So theorem 4.9 is called uniqueness of basis representation. First, let's read the theorem, then we'll explain. If a set of n vectors is a basis for a vector space, if it's B, then every vector in V can be written in one and only one way as a linear combination of the vectors in the set S. Now, this is not, and that's called uniqueness of basis representation. Now, let me tell you what it does not mean. This does not mean that there's only one unique basis for a vector space. There can be many different bases for a vector space. In fact, we'll see there could be an infinite amount of different vector spaces, of different bases for a vector space. That's for sure. I'm talking about, like, R2, R3, all these they're infinite different bases for these vector spaces. But so we're not saying that there's only one basis. When uniqueness doesn't mean there's only one basis. It means that for any particular basis that I choose, when I express a random vector as a linear combination of the vectors from this basis, there will be only one way to do that. So, for example, if I have some random vector, Bob the vector, and Bob the vector is equal to A1 V1, 3V1 plus 2V2 minus 7V3, so on and so forth. That's the only way I could combine these vectors to get my vector Bob. That's what this is. That is what this is saying. So it's not saying there's only one basis. It's saying that once I have a basis, there's only one way that I can combine each. There's only one combination of vectors which is going to produce any particular random vector in the vector space. So now let's just prove it. Well, the existence part. What do they mean by existence? Existence is, you see, it says here, one and only one way. Well, so there's two things here. There's the one, that's called the existence part, and then there's the only one, that's called the uniqueness part. So the existence portion is very straightforward, because since we know that by definition S spans the whole vector space, that's what a basis is. It spans the whole vector space. So any arbitrary vector U can be written as a linear combination of V1, V2, V3, and so forth. So so basically the existence part comes from the just the definition of a basis, that it spans the vector space. The hard part to prove is the uniqueness part. That's the real challenge. So let's do that. So to prove the uniqueness part, meaning that a vector can be represented in only one way, and that's it, not more than one way. So let's look at let's say U. Let's assume that vector U, we already know that it's C1, V1, C2, V2, dot, 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 plus C and Vn. Let's assume that, let's assume, we're going to do, before I go further, we're going to assume the opposite and then show a contradiction or show something. So let's assume it's not true. Let's assume that I could do it another way. I could represent it as B1, V1, B2, V2, dot, 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 Bn, Vn. So instead of, so here I have it all with these C scalars. Over here, I'm using B scalars. And of course, all the B's and C's have to be different from each other. Otherwise, it's the same thing. So what I'm going to do is I'm going to subtract these two equations. I'm going to subtract this equation, and I'm going to subtract that equation. So on the left-hand side, I'm going to have U minus U, which of course is 0. On the right-hand side, I have C1 V1 minus B1 V1, so that I could just factor out C1 minus B1 times V1, and then just do that all the way across. So I dot, 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 and all is equal to 0 vector. Now, we're almost done. Since we know that S is linearly independent, that means that the only solution to this equation is the trivial solution, meaning that C1 minus B1 equals 0, C1 minus B2 equals 0, dot, 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 Cn minus Bn equals 0, all the way through. But if C1 minus B1 equals 0, that means C1 equals B1. If C2 minus B2 equals 0, that means C2 equals B2. In fact, down the line, every single C3 equals B3, C17 equals B17, all the way to Cn equals Bn, which means I don't really have which means this so-called different representation really wound up being the exact same thing. I just called it, I called them B's instead of C's, but it's really the exact same thing. So so that shows it's impossible to come up, once I have one representation, it's impossible to come up with another representation. And that's what our theorem is saying. That's what our uniqueness theorem is trying to teach us. And that is awesome. Now we're just going to look at an example of this. Here's an example of this uniqueness thing that we just learned about, the uniqueness theorem. So let U be a vector in R3. So the components are U1, comma U2, comma U3. Now this big bold U is a vector. These three little, the U1, U2, U3, those are scalars. Those are just plain real numbers. And show that the equation U is equal to C1 V1 plus C2 V2 plus C3 V3. We want to show that that has a unique solution for the basis V1, V2, V3 of 1, 2, 3, 0, 1, 2, negative 2, 0, 1. Well, we actually know it already from the theorem that it must be, because the theorem just said there is a unique basis. But let's actually go through the steps and see what we got here. Let's get a feel of the babe. So from the equation, U1, U2, U3 is equal to some scalar times 1, 2, 3 plus another scalar times 0, 1, 2 plus the third scalar times negative 2, 0, 1. And if we combine these out, we distribute them. This is the same. We've dealt with these many times. We get C1 minus 2C3, C2C1 plus C2, 3C1 plus 2C2 plus 3C, just combining all the components. And this leaves us these three equations. And we could rewrite this set of equations as a matrix multiplication. So this is the coefficient matrix times the variable matrix, because we're kind of treating these as variables, and this is the B, the solution matrix. Anyway, the constant matrix, let's say. So since matrix A we know is invertible, because we've shown this, we've actually worked with this particular matrix many times. And by the way, if you're not sure it's invertible, you could always just take a you could always just do a what do you call it? You could always do a determinant and see it won't be 0. Anyway, because this is invertible, we know that this system has to have a unique solution. And the unique solution will be A inverse C is going to be equal to A inverse times U, like we've done many times. And we can verify by finding A inverse that C is going to want, if we find A inverse and do the actual multiplication, multiply A inverse times the vector U, this constant vector, we're going to wind up getting C1 is equal to negative U1 plus 4U2 minus 2U3 all the way down the line. But basically, this is just going to be different, different numbers, different scalars. So if U was the vector 1, 0, 0, that would mean that U1 is 1, U2 and U3 are both 3, and that would make it that that the vector u, which is 1, 0, 0, can be written uniquely as negative v1 plus 2v2 minus, now where do these come from? Because these, if u2 and u3 are all zeros, this whole thing disappears. This just, c1 is -1, c2 is just +2, and c3 is -1, which is what I have over here. So if I would make this combination of the vectors, of the v vectors, and the v vectors of these guys over here, I would wind up getting the vector 1, 1, 1. And you should take these three vectors here and verify that. That will be very instructive. So what I'm trying to say here is that negative times the vector 1, 2, 3 plus 2 times the vector 0, 1, 2 minus the vector 0, -2, 0, 1. These three guys right here. If I combine this and crunch it out, you're going to get 1, 0, 0. So of course, everybody do the arithmetic. It's very simple. Anyway, that's the end of part 1. We're going to continue, of course, with part 2, but that's the end of part 1, and we'll see you in the next video. Bye, everybody.